So in this video we're going to talk about quadrantal and reference angles. So a quadrantal angle is simply an angle that is written in standard position and that lands on either the x or the y axis. So for example, right here I have an angle in the xy plane that is on the positive x-axis, and this is a 0-degree angle or a 0-radian angle, and it could just as easily be a 360-degree angle. In other words, 0 degrees is coterminal with 360 degrees, and 360 degrees is equivalent to 2 pi. So in degree world, 0 degrees is a quadrantal angle, 360 degrees is a quadrantal angle, 0 radians or 2 pi radians are both quadrantal angles. Here we have an angle in standard position that is the 90-degree angle. It lands on the positive y-axis, so we have a 90-degree angle. And a 90-degree angle, like we saw earlier, we see that the upper half plane is 180 degrees, and the way that we get 90 degrees is we divide the upper half plane in 2, which gives us 90 degrees. So if this is in radian world, a full rotation of the upper half plane in radians is pi, then we just divide it in 2. So a 90-degree angle is also a pi over 2 radian quadrantal angle. Here we have the quadrantal angle 180 degrees, which is also the quadrantal angle pi radians. Here I have the quadrantal angle that lands on the negative y-axis, and this is 270 degrees. And we could kind of think about how you could calculate this. What we could do is say, hey, look, a full rotation. If I do a full rotation, that's 360 degrees. And I've only gone 3/4 of a way around a circle. So to get the angle, I could multiply by 3/4. And 4 would go in here, into 360 we would get 90 degrees, times 3 is 270 degrees. So if we're trying to identify this 275 degrees, this quadrantal angle in radians instead, what we would do is something similar. We would say a full rotation is 2 pi radians, and we have only 3/4 of that. And then we could simplify a little bit, and we'd get 1 times pi times 3 is 3 pi over the denominator numbers are, we have a 1 over here, so 1 times 2, we just get 3 pi over 2. So those are quadrantal angles, any angle in standard position that lands on the x or y axis. A reference angle for an angle is simply this. If you have a non-quadrantal angle theta, so theta needs to be non-quadrantal. The reference angle doesn't exist if the angle is a quadrantal angle, because the reference angle is always an acute angle, an angle between 0 and 90 degrees. But if the quadrantal angle exists, all it is you take your angle in standard position, here he is, and that angle, if it's not a quadrantal angle, is going to form an acute angle with the x-axis, and that acute angle is the reference angle. So if you're in quadrant 1, theta and the reference angle are one and the same angle typically, unless we've over-rotated. So the reference angle is always going to be an angle between 0 and pi over 2, between 0 and pi over 2, or it's going to be an angle between 0 and 90 degrees if we're in degree world. Pi over 2 radians and 90 degrees are the same thing. If we rotate over into quadrant 2, so here I've rotated over into quadrant 2, the reference angle is going to be the acute angle formed by the terminal side and the x-axis. So something to note, in my opinion, is that anytime you have a point on the terminal side, you can always drop a perpendicular and form a right triangle. So the reference angle is always going to be the angle for that right triangle that is adjacent the width of that triangle. And really this is a triangle that has a directed width. In other words, I have an x and a y coordinate. X's are horizontal numbers or widths, so the directed width of this, the base of it is x and the height of it is y if we allow for negative signs. If I put an absolute value sign on both these numbers, I get the height and the width of that triangle. And it's the same thing over here. Had I dropped a perpendicular from the point xy, I'd form a nice right triangle. Theta r would be adjacent the width, and x, the horizontal number, is the width, and y, the vertical number, is the height. The directed width and height, or I can put absolute value signs on those to get the width and height from a width and height perspective. So theta r, if you were going to calculate it, you can think about what you would need to do to calculate this. You can say, hey, theta is short of rotating a full 180. So to get theta r, I would take a 180 degree half rotation and subtract theta. I would say, hey, you're going to be 180 degrees minus theta. That's what theta r is going to be. Or 180 degrees is the same as pi, so I could do pi minus theta is the reference angle. And here, everything we'll notice is being labeled in radian world. Those are the quadrantal angles in radians. So the information regarding the reference angles is being given from a radian perspective, but we can convert these all over into a degree type of a world. In quadrant 3, you rotate into quadrant 3. If you drop a perpendicular to the x-axis, you get a nice right triangle, and theta r is this little corner angle. And how would you calculate it? Well, theta is an over rotation past the 180 degree mark. So you would take you would take your angle theta, the over rotation, and to get this little guy here, you would subtract off the 180 degrees. So you'd go theta minus 180 degrees to get your theta r, or theta minus pi radians to get your theta r. Finally, in quadrant 4, notice you have a nice little right triangle here. Theta r is the side adjacent the x coordinate, or the width. The width is x. The directed height is y. The height in a Euclidean perspective is just the absolute value of y. And to get theta r, what would you do? Well, if you think about it, 360 degrees would be a full rotation. You've come up short of that full rotation. You've only rotated through theta to get there. So if you subtract off theta, you'll get theta r, or 360 degrees is the same as 2 pi. So take 2 pi minus theta to get theta r. So let's try to calculate some reference angles. So find the reference angle for 820 degrees. So the first step is to find a coterminal angle between 0 and 360. That's step 1. So I'm going to take my 820 degree angle, and I want to find a coterminal angle between 0 and 360. So I'm going to go 820 minus 2 times 360. That's going to be 820 minus 720 is going to be 100 degrees. And 100 degrees lands between 90 degrees is straight up and 180 degrees is here. So 100 degrees is just past the 90 degree mark. So if I'm drawing a picture of the situation, here's a 100 degree angle in standard position. Right, here's a 100 degree angle in standard position, and the angle that we're after is this angle here, theta r. This guy right here is who we're after. So we're going to get theta r, the reference angle, by taking, hey, it's 180 degrees all the way through. We came up short of 180 degrees. We only rotated into quadrant 2 by 100 degrees. So 180 degrees minus 100 degrees is an 80 degree angle. So what we're identifying is that this angle right here between the terminal side of the 100 degree angle and the negative x-axis, that this is an 80 degree angle right there. Find the reference angle for 11 pi over 3. Typically, if we're in a pi over 3 format, typically there's the reference angle. But we'll double check. It's a pretty good possibility. But let's come up with an angle between 0. Here we came up with an angle between 0 and 360. We found a coterminal angle with 820 between 0 and 360. So here I want to make sure I have a coterminal angle between 0 and coterminal angle theta between 0 and 2 pi. And because I've got a denominator of 3, it would be nice to know what 2 pi looks like if the denominator is 3. So we'll get an equivalent ratio. 2 pi times 3 is 6 pi over 3. So 6 pi over 3 radians is the same as a 360 degree angle or a 2 pi radian angle. So it looks like we've rotated past that, and we want to subtract from this 2 pi radians until we get an angle between 0 and 6 pi over 3. So if I take 11 pi over 3 and I subtract 6 pi over 3, I'm going to get 5 pi over 3. So there's my coterminal angle. 11 pi over 3 is coterminal with 5 pi over 3. Where does 5 pi over 3 live? Well, pi over 3 says take the pi radians up here, take the pi radians or the 180 degree rotation, and divide it into 3 equal chunks. So if I divide it into 3 equal chunks, I'll get something that looks like this: 1 equal chunk, 2 equal chunks, 3 equal chunks. Those are 60 degree chunks. Break the lower half plane into the 3 equal chunks as well, and count out where does 5 pi over 3 live. 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3. There is a 5 pi over 3 radian angle, and our job is to find theta r. But a full rotation is 2 pi radians or 6 pi over 3 radians. So I would take a full rotation, 6 pi over 3, and to calculate theta r, we're going to subtract, put my equal sign in late, we're going to subtract the partial rotation, 5 pi over 3 to here, to get the little wedge that's left. So minus 5 pi over 3 is going to be pi over 3 radians for our reference angle. So same game, but now with negative angles. So again, find an angle coterminal with negative 470. That is between, find an angle coterminal with negative 470 degrees. That is between 0 and 360 degrees. So I'm going to take that negative 470 and I'm going to add to it 2 times 360 degrees. So that's going to be negative 470 plus 720. And that's going to give me a 250 degree angle. And this is 180 degrees and this is 270 degrees. So 250 is going to land in between those two. So here's a 250 degree angle, which is coterminal with negative 470. And theta r is this acute angle that this terminal side makes with the x-axis. So to calculate theta r, we realize that 250 degrees has rotated past the 180 degree mark, and we're going to subtract off 180 degree rotation to get this piece that's left. So 250 minus 180 is 70 degrees. So theta r is a 70 degree acute angle right there. Again, if I'm thinking about this as a right triangle, there's a right triangle formed by this point with the x-axis, and theta r, sorry, that's a right triangle, and theta r, 70 degrees, is this little guy right here. Find the reference angle for negative 11 pi over 3. So I think this is the last one that we're going to look at. So we have a radian rotation counterclockwise. So I'm going to take negative 11 pi over 3, and I'm going to add something to it so that I wind up with a coterminal angle between, a coterminal angle theta, that's between 0 and 2 pi radians. And remember, we can get 2 pi radians into common denominator format. And it looks like I would need to add 2 of these to get a positive angle. So I'm going to go plus 2 times 6 pi over 3, which is going to be negative 11 pi plus 12 pi. I accidentally turned the eraser on sometimes with my finger. And that's just going to equal pi over 3. And pi over 3, what does that mean? Well, pi is a 180-degree rotation. Pi is a 180. This says divide that 180 into 3 equal parts, or 60-degree chunks. So this right here is a pi over 3 angle. So initial side, terminal side. In this case, we're in quadrant 1. So theta equals theta r. So in this case, theta equals theta r equals the pi over 3 radian angle in quadrant 1.